Imagine a world where your online order just vanished into the ether, your bank balance disappeared, or maybe your favorite streaming service completely forgot your watch history. Chaos, right? But what if I told you that behind every single tap, every swipe, every digital interaction you make, there's this invisible architecture working tirelessly just to prevent that chaos? The digital world doesn't run on magic, it runs on systems, and learning to design them starts right here.
Welcome to the Deep Dive. I'm your host, and today we're embarking on a really crucial exploration. We're going into the very foundation of our digital future, database design. We're diving deep into insights from Chapter 9 of Modern Systems Analysis and Design by Valacich and George, and we're blending that academic rigor with, well, a rich collection of real-world scenarios and expert discussions to give you that insider edge.
Yeah, and our mission today isn't just to, understand it superficially. We want to truly demystify how we organize, store, and manage these just staggering amounts of data that fuel our businesses and, frankly, shape our daily lives. This deep dive is incredibly relevant, especially for those of you maybe in BCIS 3389, or really any business program where you're tasked with building resilient, intelligent systems. We really aim to equip you with the foundational knowledge to actively design robust, efficient, and truly future-proof information systems. Think of it like constructing the digital backbone that holds everything else up.
That's a great way to frame it, building the backbone. Okay, and before we unlock all these insights, just a quick request. If you find value in this deep dive, please take just a moment to like, subscribe, and share it with your network. Don't miss out on these insider tips that could genuinely position you for a bright future in your chosen career. And for even more resources and a deeper exploration of the topics we cover today, make sure to check out the description below this deep dive. Okay, let's get into it. Let's unpack the architecture. So let's kick things off by talking about the foundational role of database design. And when we say foundation, we really mean it literally. This isn't just some technical detail tucked away in an IT department somewhere. It's actually a strategic imperative that underpins every single digital application you interact with. I mean, think about it. From an e-commerce giant processing millions of transactions a second to maybe your university's student information system managing grades and enrollments, a robust database is that silent, tireless engine behind it all. And for those of you in BCIS 3389, this ties directly into the course's emphasis on the systematic analysis, design, and implementation of software systems. Laying the groundwork for the database isn't just a critical part of the system development lifecycle, the SDLC, it's arguably the most critical part for long-term success. Wouldn't you agree?
Oh, absolutely. Indeed. And what's truly fascinating here is that data modeling is the crucial first step in that systematic process. It's essentially the art and science of organizing data structures, defining their relationships, and establishing the rules that will govern your data, all to support effective database design and management. In its essence, data modeling is about making these fundamental, often high-stakes decisions right up front. Like, what specific pieces of data are absolutely necessary for our business operations? How exactly are we going to collect this data? And maybe most importantly, how should it be structured so it's both efficient and meaningful?
That sounds incredibly vital. It's almost like a pre-computation stage before you even think about writing a line of code. But what happens if a business doesn't prioritize this upfront? I mean, what's the typical fallout we see in the real world? Can you maybe give us an analogy to make that clearer?
Absolutely.
Yeah.
And the immediate practical consequences of skipping or rushing data modeling can be, frankly, catastrophic. Imagine trying to build a skyscraper without a detailed architectural blueprint. You'd have structural flaws, wasted materials, constant rework, and ultimately you'd end up with a building that might collapse under its own weight or just, fail to serve its intended purpose.
Right. Total disaster.
Exactly. Similarly, you simply wouldn't or shouldn't build a complex application without a clear data model. So the practical takeaway here is profound. A well-designed data model ensures accuracy, efficiency, and scalability right from day one. It's a set of deliberate decisions and assumptions about your data. And even if they get modified later, which they often do, it provides a crucial baseline. It helps you understand why the data is structured a certain way, it prevents costly errors down the line, and ensures your system can actually adapt and grow. And this aligns perfectly with Knowledge Outcome KO3, where students apply basic systems concepts. You're essentially conceptualizing the system's brain and memory before you lay a single brick of code, so to speak.
I really like that architectural blueprint analogy. It just makes so much sense visually. Now, you mentioned stages of data modeling. You said it's like zooming in on a map from a high-level overview down to street-level detail. So what are these stages and how do they progressively add that detail?
Yeah, that's a perfect way to put it. We generally talk about three distinct yet very interconnected stages. There's the conceptual data model, the logical data model, and finally, the physical data model. Each one represents a progressive journey of adding detail and technical specificity, moving from those abstract business requirements towards a concrete database implementation.
Okay, let's dive into the first one then. The conceptual data model, or CDM. This is the what model, right? What exactly does that mean? And importantly, who's involved in actually creating it?
Right. The conceptual data model is the highest level, most business-oriented view of an organization's data. It's often called the whiteboard model because that's often where it starts. It's precisely where you capture the fundamental ideas. Things like what core entities exist in the business domain. So in e-commerce, you'd identify things like customer, product, order. Simple enough.
Okay.
In a university system, it might be student, course, faculty. You also define their key attributes, the essential properties describing these entities, like customer name, product description, or course title. And crucially, you define how these entities relate to each other, like customer places order or faculty teaches course. What's really important about CDMs is that they are entirely technology independent. You're not thinking about specific databases yet.
Not at all. Just the concepts.
Exactly. Pure business logic. They're typically visualized using entity relationship diagrams, or ERDs, which give a clear graphical picture. The focus here is purely on capturing the scope of the system and defining those core business rules. For instance, a customer can have multiple addresses, or an order must be placed by exactly one customer. The primary audience, usually business stakeholders and domain experts working really closely with systems analysts and maybe architects, and the immense benefit. It fosters a truly shared understanding. It dramatically boosts communication between the technical folks and the non-technical teams.
Ah, that common language.
Precisely. It ensures everyone establishes a common vocabulary and agrees on the what. This collaborative process ensures the team asks the right business questions right from the start, preventing costly misunderstandings and rework later. It's about getting everyone on the same page for the grand vision.
Okay, so it's like agreeing on the big picture and the fundamental truths of the business before you get lost in the weeds of implementation. That makes a lot of sense. Okay, next up we have the logical data model, or LDM. You called it the how of the details.
Yeah.
How does this one bridge that gap between the high-level business vision and the nitty-gritty technical implementation?
Exactly. The LDM is that critical bridge. It takes those high-level concepts from the CDM and starts adding structure and technical detail. But, and this is key, it still does this without committing to a specific database technology, whether that's SQL Server, Oracle, PostgreSQL, maybe even a NoSQL database. At this stage, you're defining actual data elements, which might become tables in a relational world or collections in NoSQL. You're defining their specific attributes with defined data types. For instance, you'd specify customer ID as an integer, order date as a date field, product description might be a string of a certain length, like a varchar 255.
Getting more precise.
Much more precise. You also establish primary keys to uniquely identify records, foreign keys to link related tables, and you refine those relationships with greater precision, one to many, many to many, maybe 0 to 1 relationships. The purpose here is to help you start thinking about which type of database might be best suited for your application. If your data is highly structured with clear, interconnected relationships, maybe a relational database is ideal. If it's more flexible, maybe schemaless or distributed by nature, perhaps a document or graph database makes more sense. A major focus in the LDM is reducing redundancy and ensuring data integrity. And we do that using principles like normalization, which we'll definitely dive into next.
Normalization.
Yeah. This model is typically created by architects and business analysts. The core benefit of an LDM. It provides this flexible, platform-neutral blueprint that clarifies how the system will actually work. It promotes consistency, reduces ambiguity, and enables, agile refinement of business logic without requiring super expensive refactoring later on.
Yeah.
It's truly a detailed template for the physical database. And developing these models is absolutely central to Skills Outcome SO3. Where students implement class diagrams from business cases. You're learning to translate those abstract business requirements into a tangible, structured design.
And that brings us nicely to the final stage, the physical data model, or PDM, the how of the implementation. This sounds like where the rubber really meets the road and we finally commit to actual technology, doesn't it?
Precisely. The physical data model is the concrete, technology-specific implementation of that logical model we just discussed. This is where you actually choose your specific database management system, your DBMS, whether it's MySQL, PostgreSQL, maybe a NoSQL option like Couchbase. And here, you specify exactly how the data will be stored physically. This involves deciding on actual table names, the precise column types that the chosen DBMS understands, like varchar 255, versus maybe text-T or CLOB.
The real detail.
The real nitty-gritty. It includes defining indexes to speed up queries, constraints to enforce data rules, like not, no-rel, or unique, maybe triggers for automated actions, store procedures for common operations, and it can even get down to physical storage specifics, like whether data resides on specific disk arrays, if it should be cached in memory, how it's replicated for fault tolerance, or maybe partitioned across multiple servers for scalability. The audience for the PDM is primarily database administrators, DBAs, and developers. They're the ones actually building and maintaining the database day to day. The clear benefit here is optimization for the real world. A well-designed PDM is highly tuned for speed, efficiency, and scalability on its chosen platform. It's the final blueprint that ensures data is safely stored, organized, and accessed, making sure the system performs well under heavy load and can grow robustly with the business. It's where that theoretical elegance meets hard, practical performance needs.
Okay, so these models, conceptual, logical, physical, sound absolutely crucial for traditional database design. But how do they fit into newer, maybe more cutting-edge fields like AI applications? I mean, with machine learning and large language models becoming so prevalent, is the structured approach still just as relevant, or are we seeing a fundamental shift?
That's an excellent question and a very insightful one, especially given how fast AI is evolving. And the short answer is yes, these models are absolutely still relevant, even if their application might shift slightly or look a bit different. Think about an AI system, maybe a sophisticated recommendation engine. A conceptual data model would still be used to define those high-level entities, things like user, product, interaction, maybe algorithm, and their core relationships. It clarifies the scope of what the AI needs to understand about the world it operates in.
Okay, so the basic concepts still apply.
Exactly. Then, the logical data model would detail the specific attributes for the structured data used in training the AI, validating it, and running inferences. So for a user entity, you might define attributes like age, location, past purchase history, browsing preferences. For a product, you'd have category, price, description, features. It establishes the dataset structure, which is critical for things like feature engineering and machine learning.
Got it. Defines the training data structure.
Right. And finally, the physical data model defines the actual database schemas, maybe data lake structures, or even specialized vector databases that are optimized for performance, storage, and accessibility within the AI pipeline. This means choosing specific data stores for training data versus real-time inference data, designing for rapid data ingestion, ensuring high-speed retrieval for the AI models. So while the technologies might be different, you might be working with data lakes, vector databases, or NoSQL stores. More often than traditional relational databases, the underlying principles remain. The principles of identifying entities, attributes, relationships, and structuring data purposefully, those are fundamentally the same. The models just adapt to the specific technological demands of AI and machine learning.
That makes sense. So what's the biggest, most concise, practical takeaway for our business students from understanding these 3 levels of data modeling? Give us the quick insight.
Okay, the profound insight here is this. Understanding these 3 levels empowers you. It gives you the strategic clarity to effectively communicate with any technical team. It helps you make truly informed decisions about your organization's data strategy. And ultimately, it ensures that the business applications you conceptualize, build, or manage are founded on a solid, adaptable, and future-proof backbone. It helps you see beyond just the surface of an application to the crucial underlying data architecture that makes it all possible. And that allows you to ask the right questions at every single stage of development.
Okay, so we've got our architectural blueprints, conceptual, logical, physical models, all carefully laid out. Now, here's where it gets really interesting and sometimes a little terrifying, maybe. Let's talk about a problem that can plague any database, big or small: data redundancy. Imagine waking up one day to find the same piece of customer information stored in multiple places across your database, but with conflicting details. Sounds like maybe a minor bug. Right? Wrong. It's actually a recipe for utter chaos and can quickly erode trust in your entire system.
It truly is. Yeah, that's a huge problem. This problem manifests as what we call update anomalies, and they can introduce just terrible inconsistencies. These inconsistencies can lead to corrupted data, which then leads to bad business decisions. It's a nasty cycle. Let me break down the core issues, which are kind of like the 3 horsemen of data integrity problems. First, there's the insertion anomaly. This happens when you literally can't record certain facts until other, sometimes unrelated facts are known. For instance, imagine a course offering table that has a composite primary key, maybe like course no, instructor AD. You might not be able to add a new course no or even the course description until an instructor is actually assigned. But what if you want to simply list a new course you plan to offer next semester, but you haven't hired the instructor yet? You're stuck. You'd be forced to enter NUL values for the instructor, which often isn't allowed for primary key components, or it might violate business rules, meaning you can't even record the planned course at all. Then we have the update anomaly. This is when changing a single fact requires modifying multiple rows. And if you miss just one of those updates, which is easy to do, your data immediately becomes inconsistent. Imagine changing an instructor's office phone number. If that instructor teaches 5 different sections, their phone number might be repeated in 5 different rows in a poorly designed course offering table. Yeah. If you only update 4 of those rows, your system now has conflicting information about the instructor's content details. This is a super common source of customer service frustration. And finally, the deletion anomaly. This one is perhaps the most dangerous. It happens when deleting a row inadvertently causes other, totally separate, crucial data to be lost. Using that same course offering example. No. If you delete the last enrollment record for a particular student in a specific course offering, and if the course details, like the course description or the required textbook, are stored only with that student's last enrollment, then deleting that single record might unintentionally erase vital information about the course itself, even if other students are still enrolled. You've essentially, thrown the baby out with the bathwater.
Wow. Okay, so these aren't just minor inconveniences. They're serious threats to data reliability and ultimately business operations. The source material, Chapter 9, gives a fantastic illustration with the staff branch table example. It really paints a clear picture of this chaos. Can you walk us through that example, maybe focusing on one anomaly at a time, just to keep it really clear for our listeners?
Absolutely. The staff branch table, as presented in the sources, is a classic, almost textbook example of these anomalies in action. It's perfect for illustrating this. In the single table, details about a branch, like its branch address and telno, are redundantly repeated for every single staff member working at that branch.
Okay, I can already see the problem.
Right. It screams redundancy. So let's look at the insertion anomalies first. 1, to add a new staff member, with their staff no, name, position, salary, you must also enter the correct details for their assigned branch. Branch no, branch address, tel no. Even if that branch's details already exist elsewhere for other staff members. This forces redundant data entry and creates a really high risk of inconsistency. What if you accidentally type branch B001's address slightly differently for 2 different staff members?
Now you have 2 addresses for the same branch.
Exactly. Your data now says the same branch exists in 2 places at once, and it has 2 different addresses. Total mess. 2, even worse, what if you want to add a new branch that currently has no staff? If staff no is part of the primary key for this staff branch table, which it likely would be if staff are directly tied to branches in the structure, you'd have to enter NULL values for staff no and other staff-related columns. But this would violate entity integrity. Primary key parts can't usually be null, meaning you simply couldn't add the new branch information until you had a staff member to associate with it. You're stuck, unable to record basic business facts. Now let's consider the deletion anomalies with this same problematic table. Imagine we delete the record for, say, Art Peters, staff number S0415, who happens to be the last staff member working at branch B003. What happens then? Oh, it's right. All the details about branch B003, its address, its phone number, are completely lost from the database. They were only stored with Art Peters' record. This critical branch location data just vanishes because its last associated staff member left. You've lost an entire business location's details just by deleting an employee record. That's bad. And finally, the modification anomalies. Let's say branch B001 changes its telephone number. In this single staff branch table, you'd have to meticulously find and update every single record associated with branch B001 for Tom Daniels, for Sally Adams, for anyone else who works there. If you miss even one of these updates, your database instantly becomes inconsistent. It's providing conflicting phone numbers for the exact same branch.
So a customer calling might get an old, disconnected number or get routed wrong.
Precisely. Or worse, be given completely wrong branch information depending on which staff record the system happens to pull up. It undermines trust. The ideal solution, as the source material clearly shows, is to separate this mess into 2 distinct, well-defined tables. A staff table and a branch table. The branch no then acts as a link, a foreign key, connecting them. In the branch table, branch B001's details appear only once. Clean. And in the staff table, each staff member just has a branch. No reference pointing to the correct branch. This immediately avoids all those update issues, making your data reliable and much, much easier to manage.
Okay, that's a perfect illustration of the chaos redundancy can create. It's clearly not just an academic problem, it's a real business headache just waiting to happen. So what's our hero in this story? How do we systematically fix this mess?
Our hero undoubtedly is normalization.
Ah, normalization.
Yes. This is the systematic process we use to conquer those pesky anomalies and bring order and clarity to our data. Normalization is essentially a technique for grouping columns into tables in a very specific way. The goal is to minimize data redundancy and, as a side benefit, significantly reduce storage space. The major aim of relational database design, achieved through normalization, is to produce a set of tables that have highly desirable properties that fully support user requirements without introducing these dangerous inconsistencies. It relies on 5 key properties that any well-formed relation or table should adhere to. 1. Simple entries. Each intersection of a column and a record should contain only one single indivisible value, what we call an atomic value. No lists, no nested data, no comma-separated stuff in a single cell.
Got it. One value per cell.
2. Same set of values. All entries in any given column must be drawn from the same set of values, ensuring data type consistency. Scale all dates in the date column, all numbers in the quantity column, etc. 3. Unique rows. Every single row in the table must be unique. No identical duplicate records allowed. The primary key ensures this. 4. Insignificant column sequence. The logical order of columns in a table doesn't matter for its meaning or integrity. You can rearrange them without changing the data's meaning. 5. Insignificant row sequence. Similar, the logical order of rows also doesn't matter fundamentally. The database system can handle ordering for presentation when needed.
Okay, those are the ground rules for well-behaved tables. Now, to actually do normalization, you said we need to understand how data elements relate to each other. This is where functional dependencies, or FDs, come in, right? Can you explain that concept in practical terms?
Absolutely. A functional dependency, or FD, is a fundamental constraint between two attributes, or maybe sets of attributes. It exists where the value of one attribute uniquely determines the value of another attribute. We usually denote it as x, y, which literally means x functionally determines y, or you can say y is functionally dependent on x. X is called the determinant, often the left-hand side, LHS, and y is what's determined the right-hand side, RHS. The core rule is simple. For each distinct value of x, there can be at most one corresponding value of y. It's very similar in concept to how a primary key works to uniquely identify a whole record.
So how do we actually identify these FDs when we're looking at a business problem or maybe some raw data? What are the clues we should look for?
That's a great question. You often identify FDs directly from business rules or the problem narrative itself. Look for statements about uniqueness or direct relationships. For instance, if a user tells you, look, each course offering has a unique offering number, and that number tells us the year and the term of the offering, you can immediately infer the FD offer now, off year, off term.
Makes sense.
It also comes up naturally when you're converting an entity relationship diagram, ERD, into a table design. Each unique identifier in the ERD, a primary key or candidate key, usually becomes the determinant, LHS, of an FD, with the other attributes in that entity becoming the dependent parts, RHS.
Yeah.
Now, a critical point to remember, one that novice designers often get wrong, is the direction of the arrow for one-to-many, 1M relationships. If a business rule states a faculty member teaches many course offerings, but any single offering is taught by only one faculty member, the correct FD is offer no FMAC no.
Okay. Offer number determines faculty number.
Right. It's not fac no offer no.
Why?
Because a single faculty member, fac no, can teach many offerings, so their number wouldn't uniquely determine a single offer no. An FD must allow at most one associated value on the right-hand side for any given value on the left. Another crucial concept is the minimalism of the LHS, the determinant. Your determinant X should not contain any unneeded columns. It should be the smallest set of attributes that works. For example, if student ID determines student city, and maybe student email also uniquely determines student city, you wouldn't write the FD as student ID, student email, student city. That's redundant.
Right, pick one.
Exactly. You'd choose the most minimal determinant, like student ID, student city, or maybe student email, student city, depending on which makes more sense as a primary key or is more stable. Determinants and candidate keys must always be minimal for efficient and clear design. Now, one really important caveat to all of this. You can sometimes falsify an FD by examining sample data. If you find just 2 rows where the X value is the same but the Y value is different, boom, X does not determine Y.
But you can't prove it just from data.
Exactly. You can never prove an FD from sample data alone because you can't guarantee you have seen all possible instances or future data combinations. This is precisely where domain knowledge, the deep understanding of the business rules and how the organization actually operates, becomes absolutely essential. Without that business context, you're just making educated guesses based on incomplete information.
Okay, so we've identified our functional dependencies by carefully understanding the business rules and the inherent relationships in the data. Now it's time to put them to work through the normal forms. These are like progressive levels of data cleanliness, you said. Like climbing a ladder, you have to achieve 1NF before 2NF and 2NF before 3NF.
That's precisely it. They're a sequential journey, a series of tests or stages. Each normal form builds upon the requirements of the last one to systematically eliminate different types of redundancy and the anomalies they cause. First up, let's look at first normal form, 1NF, eliminating repeating groups. This is the baseline. A table is considered to be in 1NF if the intersection of every column and every record contains only one atomic value.
Atomic meaning indivisible.
Exactly. Indivisible for the purposes of the database. This means absolutely no nesting of data, no lists or arrays within a single cell, and no repeating groups of data across columns, like Fund 1, Fund 2, Fund 3 columns. Every cell should hold just one piece of information that can't be meaningfully broken down further in that context. A classic violation example would be that branch table we imagined, where maybe a telnos column contains multiple phone numbers in a single cell, perhaps separated by commas, like 503, 555, 3608, 503, 505, 2727.
Oh, I've seen that kind of thing.
Very common, but problematic. That single cell holds two distinct pieces of information, violating the atomic rule. The conversion process to fix this involves removing that multi-value column. You then create a new, separate table. You take a copy of the original table's primary key, example branch no, which becomes a foreign key in this new table. Then you combine that foreign key with each individual value from the original repeating group. So our branch no, branch address, telnos would become two tables, branch no, PK, branch address, and a new table, say branch telephone, branch no FK, telno PK. Now, each phone number gets its own distinct row in the branch telephone table, linked back to the correct branch via branch no. If a branch has 3 phone numbers, it will simply have 3 separate rows in the branch telephone table, clean and atomic.
Got it. Single, atomic values only. That immediately clears up some pretty common data entry issues, I can imagine. Okay, what's next on the ladder? Second normal form, 2NF, eliminating partial dependencies.
Right. Second normal form is crucial, but there's a key condition.
Okay.
It only applies to tables that have composite primary keys.
Meaning keys made of 2 or more columns.
Exactly. If a table has a simple single-column primary key, and it's already in 1NF, then it's automatically considered to be in 2NF. Yeah. So you only worry about 2NF when your primary key has multiple parts. The rule for 2NF is this. A table is in 2NF if it's already in 1NF, and every non-primary key column is fully functionally dependent on the entire composite primary key. This means no non-key attribute should depend on only part of that composite primary key. Everything else must depend on the whole key, not just a piece of it. Let's use the violation example from the source material. The temp staff allocation table. This table had a composite primary key of staff no, branch no. It was trying to combine information about temporary staff, the branches they work at, and their assigned hours. In this table, remember, branch address depends only on branch no. Branch no is part of the primary key, but it's not the whole key. So that's a partial dependency. You don't need the staff node to know a branch's address.
Right, the address belongs to the branch itself.
Precisely. Similarly, the staff member's name and position depend only on staff node. Again, staff node is only part of the primary key. You don't need the branch node to know a staff member's name or position. Another partial dependency. Only the attribute hours per week genuinely depends on both staff node and branch node. It describes the specific allocation, the relationship, of a particular staff member to a particular branch for a certain number of hours. So to convert this table to 2NF, we need to break it up. We separate the partially dependent attributes into new independent tables based on their determinants. 1, we extract branch address and its determinant branch no into a new branch table, branch no PK, branch address. 2, we extract name and position and their determinant staff no into a new temp staff table, temp staff no PK, name, position. 3, the original table then slims down to become temp staff allocation, staff no FK, branch no FK, hours per week, where staff no, branch no remains the composite primary key. Now, in this revised structure, hours per week is fully dependent on the entire composite key, and all the other attributes, branch address, name, position, have been moved to tables where they are fully dependent on their respective single-column primary keys.
We've eliminated those partial dependencies.
Okay, that makes sense. So 2NF ensures that if you have a key made of multiple parts, every other piece of information in that table really needs all those parts of the key to define it, not just some of them. That's a great step toward cleaning things up and putting data where it truly belongs. Now, for the big one, often considered the main goal for practical purposes. Third, normal form, 3NF. Eliminating transitive dependencies. This sounds like the final frontier for many business applications.
It is indeed, and you're right, it's the normal form that most businesses realistically strive for in their relational database designs. Third normal form, 3NF, states that a table must first be in 1NF and 2NF, and no non-primary key column should be transitively dependent on the primary key. Okay, what does transitively dependent mean in simpler terms? It means no non-key attribute can be determined by another non-key attribute. There shouldn't be dependencies flowing between non-key attributes within the same table.
So like a chain reaction of dependencies.
It's exactly like a chain reaction. A transitive dependency exists if you have this kind of chain. If A, B, and B, he, C, where A is the primary key and B is not part of the primary key, then C is transitively dependent on A via B. You can think of it as an indirect dependency. C depends on B, and B depends on the primary key A, but C doesn't directly depend on A itself. It depends on A through B. Let's revisit our original problematic staff branch table example, the one we discussed at the beginning before we mentally split it. Let's imagine a slightly simplified version, maybe just a staff table where staff no is the primary key, and it also contains branch no, branch address, and tel no all in the same table. Here's the chain of dependencies we identified. Staff no, branch no. We assume each staff member works at exactly one branch. So branch no depends on staff no. Note branch no is a non-key attribute here. Branch no, branch address, tel no, branch number uniquely determines its address, and phone number, branch address, and tel no are also non-key attributes.
Ah, I see the chain. Staff determines branch, branch determines address and phone.
Precisely. Because branch address and tel no depend on branch no, which is itself a non-key attribute determined by the primary key staff no. Then branch address and tel no are transitively dependent on staff no via branch no. They don't directly describe the staff member. They describe the branch that the staff member happens to be associated with. That's the transitive link. The conversion to 3NF involves breaking this chain. You separate the transitively dependent attributes, branch address tel no, along with their immediate determinant branch no, into a new table. So we end up with staff no PK, name, position, salary, branch no FK. Branch no PK, branch address tel no. Notice this is the exact same two-table structure we logically arrived at earlier, just by looking at the update anomalies. Normalization provides the systematic process to reach this cleaner, more robust design. By separating the branch details, you now have a table focused purely on staff attributes and another focused purely on branch attributes, linked correctly by a foreign key, branch no in the staff table.
That's really neat how the formal process leads to the intuitive solution. I remember seeing a really clear step-by-step example in the Wikipedia source mentioned in the outline, the one using a book table. Can you quickly touch on how that illustrates the move to 3NF? It feels like a very common real-world scenario.
Yes, that's a fantastic, very common example that makes the concept of transitive dependencies crystal clear. In that example, after achieving 2NF, the book table still had some lingering issues. Specifically, it showed these transitive dependencies. The author nationality attribute was dependent on the author attribute, which was a non-key attribute, maybe the author's name, not directly on the book's primary key, which might have been title or ISBN.
Okay. Nationality depends on author. Author doesn't depend directly on the book's key.
Exactly. Similarly, publisher country depended on publisher, another non-key attribute, and genre name depended on genre ID, where genre ID was likely just another attribute in the book table, not the key. Each of these was a non-key attribute depending on another non-key attribute within the same table, the classic sign of a transitive dependency violating 3NF. The fix, logically, was to extract these transitively dependent attributes into their own dedicated tables, centered around their immediate determinants. An author table, author PK, author nationality, publisher table, publisher PK, publisher country, a genre table, genre ID PK, genre name. The main book table then only needs to retain the foreign keys pointing to these new tables, author FK, publisher FK, genre ID FK. This eliminates those chains of dependency, puts each piece of information in its most logical single place, and brings the database design firmly into third normal form. It results in a beautifully clean, efficient, and easy-to-maintain structure.
Okay, so 3NF really seems like the practical sweet spot for most applications, getting rid of the most damaging anomalies. You mentioned there are normal forms beyond 3NF, like BCNF, 4NF, 5NF. Do we really need to worry about those in, typical business systems development?
That's a fair question. Yes, there are higher normal forms, and our source materials do mention them. Boyce Codd normal form, BCNF, which is a slightly stricter version of 3NF, fourth normal form, 4NF, fifth normal form, 5NF, and even sixth normal form, 6NF. While these exist and they address very specific, often more complex or subtle data dependency issues like multi-valued dependencies for 4NF or join dependencies for 5NF, the general consensus in industry is that third normal form 3NF is generally considered sufficient for most practical business applications.
Sufficient meaning it solves the big problems.
Exactly. For many professionals, when they say a database is normalized, they essentially mean it's in 3NF. It effectively eliminates the critical insertion, update, and deletion anomalies that plague most business systems and ensures a well-structured, manageable database. Going beyond 3NF can sometimes lead to an excessive number of tables, a phenomenon sometimes called over-normalization. This can actually make querying more complex and might even negatively impact performance in some cases without providing significant practical benefits in return for that added complexity. So the trade-off between achieving absolute theoretical purity and maintaining practical performance and simplicity often means stopping at 3NF. It hits the point of diminishing returns for many typical business scenarios.
That's a really crucial point for our business students to understand, recognizing that balance, knowing when a design is good enough for the real world versus theoretically perfect. And it really sounds like this entire segment on normalization, understanding FDs, and the normal forms is directly applicable to several of those key learning outcomes we mentioned earlier.
Oh, absolutely. This segment is critical for knowledge outcome KO4, where students learn to utilize standard UML diagrams at the database level, specifically class diagrams. Understanding normalization is really the intellectual engine behind designing those robust, meaningful class diagrams from business cases. It tells you how to structure those classes and their relationships correctly. It's also absolutely central to skills outcome SO3, where students are expected to implement class diagrams from business cases. They need normalization principles to translate the business requirements into a technically sound, normalized design represented in the diagram. And beyond the diagrams, it directly informs writing outcome W01. Students need to demonstrate their understanding of these systems analysis and design concepts, like normalization, and be able to communicate them effectively in writing. Their papers or reports would need to highlight their ability to choose appropriate analysis tools, like identifying FDs, apply them to a given case, and clearly communicate their findings, explaining why a particular normalized structure is superior to an unnormalized one, referencing the anomalies avoided. You're building both the analytical and the communication muscles vital for any systems professional.
Okay, so we've meticulously crafted our logically perfect anomaly-free data model. We've climbed the ladder, achieved that pristine 3NF where every piece of data is in its rightful atomic and non-redundant place. Feels good, right? But here's where the rubber truly meets the road. And sometimes it involves doing something that might sound like complete heresy compared to everything we just learned about eliminating redundancy. It's time to bring that beautiful logical design to life and make it actually perform well in the real world. This is where physical database design comes in. And surprisingly, as the sources suggest, it sometimes means making some strategic trade-offs that might involve carefully reintroducing some controlled redundancy.
That's a perfect way to frame it, a strategic compromise. Absolutely. Physical design is inherently technology dependent. This is a huge shift from the logical model. It's all about how to store that data efficiently and securely using a specific database management system, whether that's Oracle, SQL Server, PostgreSQL, MariaDB, or maybe even a specialized NoSQL solution like MongoDB or Cassandra. This phase requires significant collaboration. It's usually a joint effort between systems analysts who have that deep understanding of the application's needs, the data usage patterns, and the performance requirements.
Right, the what and why.
Exactly. And technical specialists like database administrators, DBAs, who intimately understand the chosen underlying technology, its efficiencies, its security features, its integrity controls, its reliability characteristics in different operating environments. This kind of team-based approach truly embodies knowledge outcome, KO5. Students will apply project management methodologies because it's a concerted, cross-functional effort involving different roles with different expertise, all working together to bring a design to successful fruition.
Okay, so what are some of the key issues or decisions that have to be made during this physical design phase, where we move from that logical blueprint to the actual tangible construction of the database?
There are several crucial considerations that directly dictate real-world performance and reliability. First, choosing data types. You asked earlier, why does selecting integer versus text matter beyond just what's stored? Well, it matters immensely. because the specific data types you choose directly influence several critical factors. Storage space. A small integer type, like small int, takes much less disk space than a large text string type, like txt or varchar max. Multiply that by millions of rows and it adds up fast. Data integrity. Choosing a numeric type prevents users from accidentally entering alphabetic characters where a number should be. A date type enforces valid date formats. Performance. Performing operations like joining two tables on an integer column is usually significantly faster than joining on long text columns. Calculations are faster on numeric types. So analysts, with their business knowledge, define what kind of data goes where. The DBA then translates that into the most precise and efficient technical data types supported by the chosen DBMS. It's a business choice, with direct technical consequences on space and speed. Then there's grouping attributes into physical records. This is about taking the attributes from your LIGO model, your tables or classes, and deciding how they will actually be physically stored together on disk or in memory to optimize access patterns. Sometimes related attributes frequently accessed together might be stored closer physically. Third, and critically important for performance, is arranging records and file organizations. This involves choosing specific techniques for physically arranging the records on the storage medium, like disk drives or SSDs, for rapid storage, retrieval, and updates. We have different types of file organizations, each with its own performance profile, its own sweet spot. Sequential file organization. Records are stored physically one after another in contiguous blocks, usually sorted in order by a primary key. This is great for batch processing, like generating a monthly report that needs to read every single record in sequence. But it's very poor for random access. Finding a single customer record quickly among millions requires scanning large parts of the file.
Like reading a book from start to finish versus using an index.
Exactly like that. Which brings us to indexed file organization. Here, records can be stored sequentially or maybe non-sequentially, but crucially, an index, a separate, smaller, table-like structure is created. This index allows the database to quickly locate individual rows based on the value of one or more columns without scanning the main table. This is excellent for rapid random retrieval, find customer ID 12345, and for sorting data quickly, which is essential for most interactive applications. Hashed file organization. In this method, an algorithm, a hash function, calculates the physical disk address of each row based on the value of a specific key, the hash key. This offers incredibly fast direct lookups if you know the exact hash key value, but can be more complex to manage, less efficient for range queries, find all orders between date X and date Y, and potentially suffer from collisions if the hash function isn't perfect. When selecting one of these organizations, the designers need to consider, according to the source, at least 7 factors. Fast data retrieval. How quickly can we get the data we need? High throughput for transactions. How many inserts, updates, deletes per second can we handle? Efficient storage space utilization. Protection from failures and data corruption. Minimizing the need for reorganization, which can take systems offline. Accommodating future growth gracefully, and ensuring adequate security controls. Each of these factors has direct business implications on cost, performance, and risk.
Okay, you mentioned indexes there with indexed file organizations. I hear about indexes all the time in the tech world, especially when talking about database speed. What exactly are they technically, and why are they so absolutely crucial for performance in these physical designs?
Right. An index, technically, is essentially a separate data structure, often organized as a B-tree or a similar structure. It acts like a specialized lookup table. Its purpose is to help the database system very quickly determine the physical location, for example, the block address on disk, of the rows in the main table that satisfy a specific condition, usually based on the value in one or more index columns. They are the key enabler for rapid random retrieval. Get me this specific record and now W. And also make sorting data much more efficient because the index itself is often already sorted. Your analogy was perfect. It's exactly like the index at the back of a large textbook. Instead of flipping through every single page, a full table scan, to find every mention of a specific keyword, you go to the index, which is small and optimized, find the relevant page numbers, the record pointers, and jump directly there. It makes searches dramatically, often orders of magnitude, faster. However, and this is the critical trade-off that every database designer and DBA must constantly weigh, while indexes dramatically speed up reads, select queries, they inevitably add overhead to writes, insert, delete, and update operations.
Why is that?
Because the index itself is a separate data structure that needs to be updated and maintained every single time the underlying data in the main table changes. If you insert a new row, you have to add an entry to the index, or maybe multiple indexes. If you delete a row, you have to remove entries. If you update an index column, you might have to update the index structure. Plus, each index consumes additional storage space, sometimes significantly so. So the art lies in creating enough indexes to support your most frequent and critical queries, but without creating so many that your write performance suffers unacceptably, or your storage costs become prohibitive. There's definitely such a thing as a too many indexes problem, where the maintenance overhead actually outweighs the query speed benefits. Beyond storage, we also need sophisticated strategies for handling queries. Optimizing the actual SQL queries written by developers to effectively leverage the chosen file organizations and the created indexes is paramount for achieving the desired real-world performance. A brilliantly designed physical database structure can still perform poorly if the queries hitting it are inefficiently written, e.g., forcing table scans when an index could be used. And finally, but certainly not least, protection and recovery. This is absolutely fundamental. It's about designing in robust controls for data integrity, e.g. constraints, data validation rules, security, access controls, encryption, backup procedures, regular tested backups, and recovery mechanisms, how to restore data after a failure. Systems analysts play a key role here too, defining things like appropriate default values for columns, range constraints, e.g. quantity must be 0, and how null values should be handled, all based on the original business rules captured way back in the conceptual and logical phases. Without these protections, even the fastest, most elegantly designed system is incredibly vulnerable to data corruption, data loss, or security breaches, which can lead to devastating business continuity issues, reputational damage, and significant financial impact.
Okay, this sounds like a tremendous amount of careful work to make our data pristine, reliable, and efficient. But then circling back to that idea I mentioned earlier, the concept of denormalization, we just spent all this time meticulously eliminating redundancy through 1NF, 2NF, 3NF, and now you're telling me we sometimes intentionally add some of it back? That honestly sounds like complete heresy to the normalization principles we just established. What's the real deal here? Is it just admitting defeat?
Uh-huh. It can feel like heresy at first glance, absolutely. But it's not admitting defeat. Rather, it's a strategic, highly pragmatic decision made firmly in the realm of physical design optimization. It's a classic performance tuning technique, a deliberate trade-off. Denormalization is the controlled process of intentionally reintroducing some carefully chosen redundancy back into a database design. It typically involves splitting tables that were perhaps combined during normalization, or more commonly, combining data from multiple normalized tables back into a single physical table, specifically to physically locate data close to one another if those pieces of data are very frequently needed together for processing, especially for read-heavy workloads.
Okay, so it's done for speed.
Primarily, yes. The main purpose is to minimize the number of expensive secondary memory I/O operations, disk reads, and reduce the need for complex joins across multiple tables, thereby significantly speeding up specific, frequently run performance-critical queries. It comes at the cost of reintroducing some redundancy, which means you might face slightly increased storage needs, and more importantly, you have to be careful about potential update anomalies, again, for the denormalized data. You need mechanisms, like triggers or application logic, to keep the duplicated data consistent. So it's a conscious trade-off between the semantic richness and logical purity of your normalized design, which is great for data integrity and flexibility, and the raw data processing efficiency required to meet performance targets in the real world. You might sacrifice a bit of that theoretical elegance for a significant, measurable performance gain on queries that are absolutely critical to the user experience or business operations. The profound insight here isn't just about optimizing, but understanding that the perfect theoretical model isn't always the perfect practical one, and that strategic controlled imperfection can sometimes be a huge asset for performance.
That's a fascinating and almost counterintuitive concept, but it makes sense when you frame it as a performance optimization. Can you give us a concrete, real-world application, maybe connecting back to our initial discussion on large e-commerce platforms and that Stack Exchange conversation you mentioned?
Absolutely. That Stack Exchange discussion about handling massive e-commerce sites with relational databases versus NoSQL is a perfect illustration of this principle in action, even if it's sometimes achieved through related techniques like caching rather than direct table denormalization. Remember Brent Ozar's advice. He suggested that for commonly accessed, rarely changing data like product catalogs, using an external caching layer like Redis is a fantastic strategy.
Right, the caching layer.
This is a classic example of applying a denormalization-like strategy at a higher architectural level, outside the database itself. Here's how it works. Your core relational database might store a perfectly normalized product catalog. Products table, categories table, attributes table, all nicely linked.
But fetching all the necessary details, name, description, price, category name, key attributes, for hundreds of thousands of products just to display a category page can be slow. It might require multiple joins and pull a lot of data from disk for every single page view.
Yeah, I can see that being slow.
So by caching frequently accessed product data, essentially making a temporary, pre-joined, readily formatted copy of some of that data in a much faster in-memory store like Redis or Memcache, you're intentionally introducing redundancy. You have the master data in the normalized database and a duplicated denormalized copy in the cache. But this redundancy is controlled and strategic. It's designed specifically for fast reads. The idea isn't necessarily to ditch relational databases entirely. As JD noted in that thread, relational databases, when architected properly with good indexing and hardware, can handle massive scale. Tens of billions of rows are achievable. But for specific extremely high-read workloads where speed is absolutely paramount, like displaying product listings or search results instantly, carefully planned redundancy, whether through caching or sometimes limited actual denormalization within the database itself, can boost performance dramatically.
When a user is browsing hundreds of thousands of products, it's often not the sheer volume that's the primary issue, but how frequently that data is accessed and how blindingly fast it needs to be delivered to provide a seamless, non-frustrating user experience. That's where denormalization principles, applied either in the database or via caching, come into play, ensuring critical data is always just milliseconds away.
So it really boils down to making smart, pragmatic choices tailored to specific use cases and understanding the performance implications of those choices. Speaking of e-commerce again, the Fusen source that was referenced laid out some great general database design best practices that seem relevant for almost any business building an online presence regardless of size. Can you quickly summarize those key takeaways for our listeners?
Certainly. Fusen highlighted several key best practices specifically for e-commerce, but you're right, they apply broadly to most database designs, especially transactional ones. Separation of records. Always strive to keep distinct business entities in separate tables. For example, customer details should be in a customers table, order information in an orders table, maybe an order items table too, product details in a products table. This leads to cleaner data management, allows for faster, more precise queries for specific information, and ensures each table has a clear single responsibility following the principles of normalization. Metadata inclusion. Don't forget to add contextual data or metadata to your tables. Things like creation timestamp, last updated timestamp, may be created by user id, product categories, user roles, or data source origin. This makes your data much more searchable, auditable, traceable, and incredibly valuable for analytics, reporting, and debugging down the road.
Good point, the who, what, when.
Exactly. Backup strategies. This is absolutely non-negotiable for business continuity. You must implement automated, regular, and tested backup procedures for all your critical data. Ideally, use cloud-based solutions or off-site storage. Recovery from technical issues, hardware failures, human error, or even catastrophic events like ransomware hinges entirely on having a robust, reliable backup strategy. Security measures. Paramount, especially when dealing with sensitive data like customer PII, personally identifiable information, payment details, or maybe personal health records. This means implementing strong, granular access controls, who can see or modify what data, using encryption for data both at rest, on disk, and in transit over the network, and conducting regular security audits and perhaps penetration testing to identify vulnerabilities. Flexibility and integration. Design your database with an eye towards future growth and interoperability. Try to make sure it can easily connect with other essential business systems like your CRM, customer relationship management system, your analytics platforms like Tableau or Power BI, or your inventory management systems.
This fosters a more holistic view of your business operations, enabling better insights and more informed decision-making across the entire organization. Following these practices helps build a system that's not only secure and fast today, but also scalable, adaptable, and a true strategic asset for any growing business tomorrow.
Those sound like incredibly solid principles that could save businesses a lot of headaches, maybe even prevent failures. But sometimes the best learning comes from seeing where things went wrong, especially in the Wild West days of early e-commerce. The UW course's web server source provided a fascinating real-world case study from Garden.com, one of the early internet retailers. What critical lessons can we draw from their experience about the importance, or perhaps the neglect, of physical database design?
Oh, Garden.com is a powerful, almost classic cautionary tale. It perfectly illustrates what happens when physical database design isn't prioritized from the start, or perhaps more accurately, when it doesn't keep pace with rapid business growth and increasing load.
As the company grew, their primary crippling complaint became dramatically slow database performance. This wasn't just a minor technical inconvenience, it translated directly into a poor user experience, frustrated customers abandoning carts, and ultimately lost sales and damaged reputation.
The bottom line impact.
Absolutely. And a significant contributor to this crippling slowness was identified as a glaring lack of indexes on columns used for common lookups. For example, customer service representatives trying to look up users or their order history faced terrible delays because the database likely had to perform full table scans. When the database was small, early on, this wasn't a noticeable issue. The scans were fast enough, but as the data volume exploded with scale, the flaw was brutally exposed. Performance ground to a halt. It got so bad that the CTO had to resort to making extensive use of caching, creating, as the source mentioned, a staggering 300,000 individual cache files on every single web server just to try and mitigate the overwhelming load on the underlying database.
Wow, that sounds like a desperate measure.
It really does. It highlights that the fundamental database design itself wasn't optimized for the workload, necessitating a complex, resource-intensive, and likely hard-to-manage workaround just to keep the site usable. The discussion around Garden.com also touched on the critical need for effective monitoring systems to actually spot performance problems before they become critical, and the importance of having flexible, programmable architectures, like the mention of the CVS Java debate in the source, that allow developers to adapt and optimize system components to handle changing workloads and performance demands. This whole Garden.com example starkly underscores that physical database design decisions, things like choosing the right file organization, creating appropriate indexes, anticipating growth, have direct, tangible, and often severe impacts on system performance, user experience, operational costs, and ultimately a business's ability to succeed or fail. It directly relates back to those learning outcomes.
KO1, applying economic models to understand the trade-offs between performance investment and business cost benefit. KO2, recognizing the need for organizational models that support seamless team collaboration between business, analysts, and DBAs in design. And KO3, applying systems concepts like efficiency, scalability, and bottlenecks. And is also a perfect sobering example for WO1, demonstrating the ability to communicate complex technical decisions, or the lack thereof, and their profound business impact. It powerfully shows that it's not just about what data you have, but crucially, how you organize and optimize it to actually support your business goals effectively at scale.
That's truly fascinating and a bit scary. What's striking is that the core problems Garden.com faced weren't necessarily about a lack of data, but maybe a lack of design foresight for handling that data efficiently at scale and anticipating future needs. So just to bring it home, if a modern system architect or analyst were faced with a similar business model and those kinds of rapid growth expectations today, what would they likely do differently based on what we know now about physical design?
That's a fantastic question, and it really highlights how much the field of systems analysis and design, particularly around database architecture, has evolved. A modern architect would approach it with a design for scale and design for performance mindset right from day one. They would likely 1. Prioritize performance modeling and testing. Instead of waiting for users to complain, they'd use tools to simulate expected load and proactively identify potential bottlenecks in a database design before launch. 2. Implement strategic indexing. They wouldn't just index primary keys. They'd analyze expected query patterns and implement indexes on foreign keys, frequently filtered columns like status or data range, and columns used in common joins based on anticipated user behavior. 3. Build in a layered architecture with integrated caching. Rather than resorting to ad hoc cache files later, they would likely design a robust distributed caching layer using technologies like Redis or Memcached as an integral part of the system architecture from the beginning. This would be used as a planned strategic denormalization approach for high-read, low-write data like product catalogs or user session information.
Planned redundancy, not desperation.
It's exactly. Planned, managed redundancy for performance. 4. Consider database sharding or partitioning early. For truly massive scale expectations, they might proactively design the database to be horizontally partitioned or sharded from the outset. This means dividing the data across multiple database servers or instances to distribute the load and improve performance and scalability long term. 5. Leverage cloud-native database solutions. They would strongly consider using managed cloud database service like Amazon RDS, Azure SQL Database, Google Cloud SQL, which offer built-in scalability features, read replicas, easy resizing, automated backups, high availability, and performance tuning advisors, reducing the operational burden. 6. Implement comprehensive observability and monitoring. They'd integrate robust monitoring, logging, and alerting tools like Datadog, New Relic, or Prometheus Grafana from the start. This allows the team to track key database performance metrics, identify issues proactively, and address them often before they significantly impact users. So the modern approach is much more proactive, data-driven, and leverages more sophisticated architectural patterns and tooling. It's not just about collecting data, but about architecting its storage, retrieval, and management to ensure it remains a performant asset, not a crippling liability, and can evolve gracefully as the business inevitably grows and changes. Hashtag tag out tag outro.
Wow. Okay. So if we just take a step back and recap our journey today, we started with the high-level what of conceptual models, moved through the detailed how of logical design and normalization, and finally landed in the pragmatic, real-world how of physical design and optimization. We've really explored how this seemingly abstract topic of database design is actually the fundamental bedrock of pretty much every digital experience we have. We've seen how meticulously organizing our data using things like normalization prevents that chaos of anomalies, ensures integrity, and then how we strategically optimize for speed and efficiency in the physical realm, sometimes even needing to embrace that idea of controlled redundancy through denormalization or caching. It's about knowing the rules and sometimes knowing when and why to carefully bend them.
Precisely. And the key takeaway really is that a well-designed database isn't just a technical checkbox. It's a fundamental, ongoing investment. An investment in the security, the dependability, and the future-proofing of any organization that relies on data, which is pretty much everyone now. It's about empowering businesses to ask the right questions of their data, to gain deep, reliable insights, and crucially, to scale their operations effectively without being constantly crippled by data inconsistencies, security breaches, or performance bottlenecks. At the end of the day, it's often the difference between a thriving, agile digital enterprise and one that's constantly struggling just to keep up with its own data challenges.
So the next time you tap your phone, swipe your card, or click that Buy Now button, just take a second and remember, the digital world isn't running on magic. Not at all. It's running on carefully designed systems, built on data that someone, somewhere, meticulously organized, normalized, and optimized. And that someone could absolutely be you.
Yeah. And considering the breathtaking speed at which technology continues to evolve and the absolute explosion of data coming from new sources like AI applications and the Internet of Things, maybe the final provocative thought to leave you with is this. As you design systems, constantly ask yourself, is what I'm creating today going to become the next piece of expensive, hard-to-fix tech debt for this organization? Or am I building a truly valuable, adaptable data asset? Building effective, resilient database solutions isn't a one-time task you just finish. It's really a continuous commitment to owning your career growth, embracing lifelong learning, and challenging yourself to build better, faster, and more intelligent systems in a world that constantly demands exactly that. That critical thinking, that foresight, is perhaps your most valuable asset.
That's a great challenge to end on. Thank you so much for joining us on this deep dive into database design. We really hope you found this valuable and insightful. If you did, please do us a favor and like, subscribe, and maybe share this with colleagues or classmates who might benefit. And please don't forget to check the description below for even more resources and links related to systems analysis, database design, and the topics we discussed today. Behind every tap, swipe, and click is a system that someone designed. Until next time, keep building the future one process at a time.